Now that we have covered several examples of electrophilic aromatic substitution, let's take a look at how substituents affect the reactivity of the aromatic ring in electrophilic aromatic substitution reactions. We'll use the nitration reactions as an example. Note that when we have just a benzene ring, so that would be the first entry here, the relative reactivity or relative rate of reaction is 1. When we introduce a methyl group there, so in other words, we're using toluene, the reaction is almost 25 times faster. When we use phenol, the reaction is about 1,000 times faster. So we consider a methyl group and a hydroxyl group activating groups. In other words, they speed up the reaction. They activate the aromatic ring in terms of the electrophilic aromatic substitution reaction. A halogen, like chlorine, will deactivate the aromatic ring, so it is much slower when we use a chlorine on benzene. And when we use a nitro group, the reaction is even slower. So both a halogen and a nitro group are deactivating groups in terms of the electrophilic aromatic substitution reaction. Electron donating groups or activating groups are generally going to make an aromatic ring more electron rich. And so that means that the ring would be more nucleophilic. It also means that the carbocation in the sigma complex is more stabilized. It also means that the activation energy will be lower for the rate determining step, which is the formation of the sigma complex. Deactivating groups, which are electron withdrawing groups, will do the opposite. They will make the ring less electron rich, which means it will be less nucleophilic. It also means that the carbocation or the sigma complex will be destabilized or higher in energy, which will lead to a higher activation energy for the rate determining step. There are many function groups that can be added to an aromatic ring, which will affect the reactivity of that aromatic ring. In general, alkyl groups and other phenyl groups will make the ring activated. Other atoms that have lone pairs in general will make the ring also activated, more so than alkyl groups. So for example, a methoxy group, an amino group, a phenol group, an ester or an amide that has a nitrogen or an oxygen directly attached to the aromatic ring will also activate the ring. Halogens in general will deactivate the aromatic ring. Carbonyl functional groups or other highly electron withdrawing groups will deactivate the ring as well. So the reactivity goes in this direction, where these are the functional groups that make the ring even more reactive, and these will make it less reactive. Let's now go through several examples of functional groups and how they are categorized as far as activation of the aromatic ring. Functional groups that have an oxygen or a nitrogen directly attached to the ring will generally be considered strongly activating groups. For example, phenols, amino groups, ethers, and other substituted amino groups. Although these have highly electronegative atoms, which you would think would make the ring less electron rich by withdrawing electron density, they're actually considered electron donating through resonance. The phenol, as an example, can donate electron density into the ring as shown here. So the lone pair can push electron density specifically to the ortho and para positions. So one of the resonance forms shown here will have a negative charge at that ortho position, which we can draw another resonance structure which will place that negative charge at the para position or at the other ortho position. Again, these functional groups make the ring more electron rich, which means it's more nucleophilic. It means that the carbocation intermediate is more stabilized, and it means that the activation energy for the rate determining step is lower. Esters and amides are considered moderately activating groups as long as the oxygen or the nitrogen is directly connected to the aromatic ring. Although we have a highly electronegative atom like oxygen or nitrogen, which are considered electron withdrawing groups in general, these are overall electron donating groups because of resonance. So very similar to the phenol example, the lone pair on this oxygen can donate electron density towards the ring. Same thing for the lone pair on this nitrogen, which can donate electron density into the ring. Alkyl groups or phenyl groups are considered weakly activating groups, and they do this primarily through hyperconjugation. So when you have a methyl group, for example, in the sigma complex, one of the resonance structures will have a positive charge directly on the same carbon as the substituent, in this case a methyl group. And that will lead to stabilizing that carbocation through hyperconjugation, compared to an example where we don't have that methyl group, instead we have a hydrogen. That would be a less stable carbocation. Halogens in general are considered weakly deactivating groups. Fluorine is too highly electronegative to be able to donate electron density through resonance like an oxygen or a nitrogen in phenol and aniline. The other halogens don't match orbitals very well since they're lower in the periodic table, and so they are not able to donate electron density into a carbon, which would be a part of the aromatic ring. So overall, the halogens, although they have lone pairs like oxygen and nitrogen, because they're electronegative or more electronegative, or they are too big of an atom, they're generally not able to donate electron density into the ring as well as oxygen and nitrogen. Carbonyl compounds are considered moderately deactivating, for example, aldehydes, ketones, esters, carboxylic acids, and amides. Note that we previously talked about how esters and amides are activating groups, but that is only when the oxygen or the nitrogen of these functional groups are directly connected to the aromatic ring. When it is the carbonyl that is connected to the aromatic ring, they're considered deactivating groups. Other groups like nitriles, nitro groups, quaternary ammonium groups, and sulfonic acids are considered strongly deactivating. All of these groups are deactivating through both induction as well as resonance. Using the ketone as an example, it is deactivating because we have highly electronegative atoms like oxygen. And also because of resonance, if we draw a resonance structure that pushes electrons towards the oxygen of the carbonyl, we create this resonance structure that has a positive charge at either the ortho or at the para position. Substituents on an aromatic ring not only affect the speed of the reaction, in other words, some of them are considered activating while others are deactivating groups, but they also affect the orientation of a new substituent whenever we do an electrophilic aromatic substitution reaction. As a rule of thumb, activating groups are generally going to give you mostly ortho and para substitution, while deactivating groups will give you primarily meta substitution. The one exception to that rule is halogens, which are considered weak deactivators. They will also give you ortho and para substitution. Here's an example involving nitration. When we use moderate and strongly deactivating groups like carbonyls and nitro groups and nitriles, we see primarily meta substitution. When we use the halogens, which again are weak deactivators, these give you primarily ortho and para substitution. As you can see by these examples, primarily ortho and para substitution. And moderate, weakly, and strong activators will all give you primarily ortho and para substitution, as you can see by these examples. As mentioned before, in general, all activating groups will give you primarily ortho and para substitution. So as an example, an ethyl group, which is considered a weak activating group, will give you primarily ortho substitution when we do a chlorination, as well as para substitution. Deactivating groups in general will give you meta substitution. This is especially true for moderate and strongly deactivators. So a nitro group, which is a strong deactivator, when we do a halogenation like bromination, we would get primarily meta substitution. The exception to that rule is that weak deactivators, which are the halogens, will generally give you ortho and para substitution. As an example, if we had a chlorine and we did a nitration, we're going to get primarily ortho and para products. Let's look now at the reasons why certain functional groups will give you primarily ortho and para substitution, while others will give you primarily meta substitution. We'll start with weak activators, for example, alkyl groups. These are primarily ortho-para directing. The reason for that is one of the resonance structures that is formed from ortho substitution has a highly stable carbocation, which has the carbocation directly on the same carbon as the methyl group. The same thing occurs in para substitution. One of the resonance structures, so there are three, one of the resonance structures is highly stable because we have a carbocation that is on the same carbon as the methyl group. When we do meta substitution, which rarely occurs, we never have a resonance structure that has the carbocation directly where the methyl group is. So we don't have a highly stable carbocation intermediate, therefore meta substitution does not occur, or at least not to the same extent as ortho and para substitution. When it comes to the moderate and strong activators, which would be, for example, phenol, we generally see ortho and para substitution. The reason for that is when we do ortho substitution, we have an extra resonance structure, so there are 4 versus 3 that we see in meta substitution. One of those 4 resonance structure when we do an ortho substitution also has a full octet on every atom. So the oxygen and carbon, as well as every other carbon in the ring, has a full octet. That makes this a very stable resonance structure, more so than the other ones. We see the same thing with para substitution. We have 4 resonance structures. Generally, when we have more resonance structures, that pathway would be more likely to occur. Also, one of the resonance structures has a full octet on every atom that is part of the molecule, and so this is a highly stable resonance structure. You might recall that the weak deactivators, which would be the halogens like a chlorine, are generally ortho-para directing, even though they are deactivating groups. Very similar to the phenol example, when we do an ortho or para substitution, we're going to have 4 resonance structures. In the case of a meta substitution, we get 3 resonance structures. So again, in general, the more resonance structures we have for very similar intermediates, the more stable that resonance or that intermediate will be. In addition, one of the resonance structures when we do ortho or para substitution is highly stable because there's a full octet on every atom. Moderate and strong deactivating groups are generally going to direct a new substituent to the meta position. The reason for this is when we do ortho or para substitution, we're going to end up with a carbocation intermediate that has a resonance structure that involves a carbocation directly attached or on the same carbon as the strongly deactivating group, so the highly electronegative group. For example, with an aldehyde, if we did an ortho substitution of a nitro group, we're going to have this positive charge on the same carbon as the carbonyl. So this is a very unstable resonance structure. We have a similar resonance structure when we do para substitution, where the positive charge is on the same carbon as the carbonyl. In the case of meta substitution, the positive charge will always be away, at least one carbon away from the carbonyl. With substituents that direct a new substituent to the ortho and para position, we generally end up with two possible products. The exact ratio between these two products will depend on the substituents. For example, if we have a methyl group already on the benzene ring and we try to do a nitration, we're going to get approximately a 2-to-1 ratio between the ortho and para product. Notice that this is based on primarily statistics. So there are two ortho positions, there's only one para position, so it makes sense as long as both the existing functional group, which is the methyl, and the new substituent are relatively small. In other words, they both have very low sterics. The ratio of the products between ortho and para should be relatively close to a 2-to-1 ratio. As the size of the existing groups increase, for example, if we replace the methyl group with an ethyl group, the ratio will go down closer to being a 1-to-1 ratio, or in some cases, preferring the para substituted product. So with an ethyl group, we get a 1-to-1 ratio between ortho and para products. With a curved-butyl group, since it's such a large group, it blocks the ortho position to some extent, and we get primarily para substitution. In this question, we're going to predict the 3 possible isomers that would occur from the monobromination of toluene, and then we're going to predict which is the most likely product from the 3. This question is basically asking us to draw the ortho, the meta, and the para substituted products once we add bromine to toluene. So Br2 and iron tribromide would add a bromine to either the ortho, meta, or para position, and giving us these 3 isomers. Since a methyl group is a weak activating group, generally it's going to direct any new substituent to the ortho and para position. So the primary products should be the ortho and the para products. And if I had to guess, since bromine and a methyl group are relatively small groups, I would suspect that the main product would be the ortho product in this example. In this question, we're going to try to predict the major product from the nitration of bromobenzene. Bromobenzene has a weak deactivating group, which is a ortho-para directing group. So when we do a nitration of bromobenzene, we should expect primarily ortho and para substitution. Since the nitro group and the bromine are relatively small, I would suspect that the ortho substituted product will probably be the major product. In this question, we're going to try to explain why the Friedel-Crafts alkylation often gives multiple substitution products, but the Friedel-Crafts acylation does not. And there's an example shown here with benzene and methyl chloride. When we do an alkylation, we get a single substituted product as well as a di-substituted product. When we do an acylation, we get only a single substituted product. You might recall that alkyl groups, like a methyl group, are activating groups. They're weakly activating groups. And so the product from this reaction is actually more reactive than benzene, since it has an activating group on the benzene ring. So it makes sense that once we do a single alkylation, the product would continue to do other alkylation reactions as long as there's enough alkyl halide and the acid catalyst. So that explains why we not only do we get a single alkylated product, but a product that has two alkyl groups. When we add a acyl group or a ketone, this product is now less reactive than benzene since it has a deactivating group, a moderately deactivating group. And so the product that we see here is not going to want to do another substitution since it's less reactive than benzene. This question is asking us to do a synthesis of metachloronitrobenzene from benzene. In order to synthesize metachloronitrobenzene from benzene, we would have to do a chlorination and a nitration. Often when we do one of these synthesis examples involving a substituted benzene compound, we want to think about what each functional group does in terms of directing the new substituent. And so we want to obviously do a nitration and a chlorination, but we have to choose one of them first, perhaps, since the other one may lead to the wrong isomer product. If we do a nitration first, we would add a nitro group, and you might recall that the nitro group is a meta-directing group, and so the chlorine would add to the meta position, giving us the desired isomer. However, if we try to do a chlorination first, the chlorine, you might recall, is an ortho-para-directing group, so if we do the nitration after the chlorination, then we would end up with an ortho or a para substituted isomer instead. In this question, we want to explain why acetylide, which is the molecule shown here, is less reactive than aniline towards electrophilic aromatic substitution. So this question is asking us to explain why acetylide, which is the molecule shown here, is less reactive towards electrophilic aromatic substitution than aniline. Aniline, you might recall, is a compound that has benzene with an amino group attached to it. Now, there are many ways to explain the reactivity, the difference in reactivity between acetylide and aniline. One of the ways is that the lone pair on the nitrogen can donate electron density into the ring as shown here, and the negative charge that is created in the ring can be moved around the ring through other resonance structures. We would do something similar with aniline. The difference is that the lone pair on the nitrogen of acetylide is actually also tied up in resonance with the carbonyl of the amide. So we can draw another resonance structure which involves moving the electrons towards the carbonyl to create this other resonance structure. We wouldn't do this with the aniline. And note that this structure, this resonance structure, is actually more stable since we have a negative charge on the oxygen compared to the other resonance structures that we see here. with a negative charge around the carbons. So in the case of acetylide, the lone pair is actually tied up in resonance with the carbonyl, while in the case of aniline, that lone pair, since there is no carbonyl, is free to push electron density into the ring, which makes the ring even more electron rich than it would be in acetylide.